Okay, well, welcome. This talk is going to be about Apache ActiveMQ and connecting applications everywhere. My name's Rob Davies. I work for Red Hat currently. So this is me. I'm a technical director at Red Hat, particularly for Fuse technology, and I was previously the CTO of FuseSource. We were acquired by Red Hat officially last October. So I've been with Red Hat about 6 months now. And I work on primarily ActiveMQ, some bits of Camel. I founded Apache Service Mix. I'm on the expert group for JMS 2 or JSR 343, and I'm co-author on ActiveMQ in Action. So what I'm going to talk to you today is really about why is integration and messaging important. And there's a number of reasons, but it all boils down to one fundamental thing. Enterprises need to know everything about their organization. So I had this conversation a couple of years ago with an analyst at Java 1 in San Francisco. And he was saying to me that basically, with things moving to a SaaS kind of model, integration is going to go away. No one's going to need to integrate with anything. But actually, the opposite is true, because we now have 10,000 SaaS providers. There's about 8,000 public APIs, and there's more things to integrate with. And if you combine that with the amount of interconnected devices, 50 billion by 2025, if you believe Forrester, then we need more messaging and integration, unfortunately. So I'm going to talk about that particular case. I'm going to go through bits and pieces around ActiveMQ, which makes it worthwhile in terms of an integration technology. Some problems which may occur if you're using ActiveMQ in large deployments. And I'll finish up talking about some new projects which we've been developing as a group within Red Hat. But first of all, I'm going to talk about messaging and ActiveMQ. So why use message-oriented middleware? But really, there's a few fundamental things. Really, it's robustness to change. So you can have disconnected applications. It means that you do not have to be, when you start communicating with your peer, another application, you don't have to be concerned about where it is. You can use location independency and also time independency, because a message broker will act as an intermediary in the middle to take care of that messaging for you. It's a bit like the post office. You send something to the post office, and you don't care when it gets there. You know it's going to get there. If you want to, though, you can also get a receipt back to say it's been delivered. And there's those kind of concepts which are built into modern-day messaging. So what actually is ActiveMQ? Hang on. So let's start this again. So what's ActiveMQ? ActiveMQ is a top-level Apache project. It's been there for about 7 years. It was actually founded in 2004 in Codehouse. It's now got about 40 developers on it, 11 who currently work at Red Hat. But it also provides internet connectivity into other languages, not just Java, but C++, C, .NET, and because it uses something called Stomp, it allows connectivity into a lot of other different languages like Ruby, Python, Perl, ActionScript, etc. Lots of different connection options. So before I go into more about ActiveMQ, I'm just going to explain some messaging basics. For messaging, the concept of a message channel is a route in which you send parcels of information. Those parcels of information are contained in a message. And those messages are passed down message channels. And in JMS parlance, a destination is equivalent to a message channel. And you can tune into message channels with things like wildcards, and you can fine-tune what you receive from a message channel by using things like selectors. You can also route messages based on the content of the actual message itself. And in particular, in a project I'll talk about in a bit more detail later on, Apache Camel makes that really powerful, a really powerful combination to make that actually happen. So here's an example of message channels with destinations. And if you can see on this example here, a producer here is sending to the destination order, and in it, only that consumer which is attached to that destination is going to receive that message. So it's not broadcasted out, it's actually restricted to the destination that that particular consumer is listening on. That's another important concept as well with destinations, and that's there's two things, point-to-point and publish-subscribe. Point-to-point, the messages get round-robined around the consumers. So not every consumer gets the same message. It gets evenly distributed with some caveats to each consumer which is available to consume it. And in ActiveMQ, it doesn't just do a round-robin. It also looks at the load a particular consumer is under before distributing out that message. That's completely different to topics. In a topic, all the consumers listening on that particular topic will get the exact same copy of that message. So let's take that down a notch and talk about selectors. So this is an example of a selector. One selector for particular consumers looking out for blue messages. The other one is looking out for red messages. And as you can see, they're both listening to the same destination, but because they've got that finer level of control, they can select messages based on properties in the message header. So I talked about tuning into message concepts, and something you can do is to actually tune in to destination types. And ActiveMQ supports wildcard hierarchies. This is quite a common concept for messaging products. And so, for example, if I have a producer which is sending to a particular topic called bar wine, then that consumer, because it's using a wildcard, that greater than, will receive any drinks or any messages going towards that particular topic bar. It's also another concept that we have in ActiveMQ, and that's called exclusive consumers. And normally with a queue, you want to round robin messages between things. But what about if you want to preserve order over messaging? So you want messages to come and processed in a particular order. Ideally, you want those to go to one consumer only. And that's why we support the notion of an exclusive consumer. Exclusive consumers are actually set by the consumer when it connects to the broker, and it actually gives a hint to the message broker that it's going to be the exclusive consumer on this particular queue. So what the broker will do, and if it's got multiple exclusive consumers, it put them all into a pot, and it will pick the first one which attaches. So in this particular case, with an exclusive consumer, all the messages will just go to that one consumer. However, if that consumer dies or gets closed down, then another consumer will get used to be the exclusive consumer. Now that's all very well and good, but it means that you've got consumers sitting out there in your network which aren't actually doing very much, apart from waiting for the main exclusive consumer, the master consumer, to either close or die or get disconnected from the message broker. So we've got this concept of message groups, and you can think of those as parallel exclusive consumers. And what you do there, you need some application kind of logic on the producers. But for each message you send, you set a special header property, which is the JMX group ID, which just takes a string. And on that string, you give it a unique reference, like it could be stock price, for example, if you want that to be processed. So here's an example of starting a group. It's creating a text message and sending hi from DevOps to this particular group, which will only be consumed by one consumer. And if you actually want to close a group explicitly, then all you have to do is send JMX group sequence ID of -1. Now on the consumer side, when you're receiving these messages, what you actually see is a stream of messages. So you won't actually necessarily start off at sequence 0, because it depends on when you started that conversation. But you can be guaranteed that if you start receiving messages on a particular group ID, then you're the only consumer up receiving those messages. So just like an exclusive consumer, a broker round robin around any consumers listing on a particular destination and then break up the groups accordingly. So that's the fundamental concepts behind kind of messaging on a high level. And then ActiveMQ itself, one of the reasons it's become so popular is because of its flexibility in deployment. One of the most important things is you can run it embedded, which means it's very easy to run inside a JUnit test. It means you don't actually have to use any mocks. You can actually use a message broker itself. It runs standalone as well, so it can be form part of a high available message cluster if it needs to. Or it can be deployed in Tomcat as a WAR or in a JEE server. It's either a client or actually embedded if you're using JCA. And actually ActiveMQ distributes a RAR for that particular purpose. So let's talk a bit more about some of the more basic concepts of messaging, which is denoting the quality of service. And one of the key things here, apart from ActiveMQ supports transactions, but one of the fundamental concepts of quality of service is defined away around how that message is delivered. And it follows the concepts in JMS. There's two types of delivery mode. It's quite basic. It's persistent or non-persistent. And if you mark a message as persistent and you're sending it into a queue, it will always get stored by the message broker to be delivered at a later time to any interested clients. For topics, it's slightly different. For topics, you actually have to register an interest in that particular topic with a durable subscriber first. So a durable subscriber has to register first or use management API to say, I'm going to create a durable subscriber on a particular topic. And in that case, any messages which get sent to that topic will be persisted on disk to be delivered later. So, how this actually looks on the disk storage for queues, it's very straightforward and simple. Because we know there's only ever going to be one consumer for a particular queue message, we can actually store them like a queue. It gets a bit more complex if you're talking about topics, because you're actually having potentially multiple subscribers on a particular topic listening to the same messages. So rather than take the hit and the overhead of copying the message every single time for every durable subscriber, there's one actual queue construct which has the actual real messages, and then there's another queue which references in to the physical message queue with references for the durable subscriber. So that adds a bit of complexity about how messages are stored. And all the message stores that ActiveMQ supports fall down into these basic kind of concepts. There's a cache which exists in the message broker. So that's there really for optimal performance. Any messages which come in which can stay in the cache will stay in the cache until they can be delivered. But they stay in the cache only after that message has also been persisted to disk. We also support indexes, and these have different structures too. I may reference the messages stored on disk in transactional logs. ActiveMQ actually supports many different message stores. SQL through JDBC is slow but popular. I mean, usually we have people who are using ActiveMQ with Oracle, for example, as a backend. The message store and Kaha are depreciated now. We've gone through a lot of iterations with different message stores as we've been trying to find the most optimum one. Right now, the default is KahaDB. And that's kind of been around and used by the community for a number of years and by people in production for a number of years. And that's the most stable. But the best one is something that is we've been working on for the last 18 months. It's called the LevelDB store and uses the LevelDB index, which has been developed by Google. So if we look at the internals of CarHireDB, this is showing like the generic store, but in slightly more detail. We have B-tree indexes which are stored on disk. But we found one of the problems was with other message store implementations were if that index got corrupted, then to rebuild up that index again, we'd have to trawl through all the message logs to actually build up that index. And that could take a long time. We have applications which could have hundreds of millions of messages, and this has been the case where we've seen people in production who've lost their index for whatever reason, and they have to try and rebuild it up again, and that can take hours, even days sometimes, if the message database is that big. So in CarHireDB, there's a redo log added to the B-tree indexes, so we can do the redo log is snapshotted at the same time as transaction log, so we can replay messages into that index and build it up at a much quicker rate. So if you compare recovery times with CarHireDB to previous versions of a message store, it's the maximum a few minutes compared to the hours it potentially could have been before. So I talked about LevelDB, and the reason that we've looked at LevelDB is we've continually trying to optimize message storage for ActiveMQ and make it faster, or as fast as we possibly can. It has fewer index entries per message than CarHireDB. It has a more performant B-tree index, and it also optimizes the way it actually does garbage collection around the B-tree index. So just to give you an example of how that actually works out in terms of raw performance, we've tested CarHireDB against LevelDB with very small messages, so we're not incurring the overhead of a large message on disk. It's really actually trying out the different storage implementations of the databases themselves. And as you can see, LevelDB far outperforms CarHireDB and all the things you want to do with a message database, be that enqueue, dequeue, drain in queues, etc. So currently, CarHireDB is the default for ActiveMQ. ActiveMQ is now at 5.8. We're going to start introduce. We've started to introduce LevelDB. The next version, 5.9, which will be out in a few months, we're going to start moving people over to that as being the default database. And obviously, we're going to put the migration tools in place to make that happen. So something else which is important about integration, particularly when using messaging, is the number of messaging protocols that you use. By default, we use OpenWire, which is an ActiveMQ kind of native protocol. It's used with our Java clients and our .NET and C++ clients. The benefits OpenWire gives us is that we have direct control via OpenWire with commands from the broker. So we can do things like client reload balancing from commands we get from the brokers. So you have a cluster of brokers, and the new broker gets introduced into that cluster. We can order all our clients to rebalance themselves across the cluster. And that's something that we do currently using OpenWire. Something else which is really useful is the failover protocol, which is built into OpenWire. So OpenWire supports itself the notion of liveness. So it knows there's a ping protocol built into it. And we can also tell when clients are failing over because of OpenWire and flipping between brokers, and we can prevent that happening. We also can do more advanced things like flow control, so we can pass back pressure on to producers which are producing messages too fast. So it's been fine-tuned over time, and it's the default message protocol used by ActiveMQ. However, there are a few others which are important. MQTT, the MQ telemetry transport, is important for the Internet things. It's a protocol which has been developed by IBM, and it's been moved to Oasis as a standard. And it's there in place to take account of all the connected devices that is going to be available on the internet over the next 10 years, 10, 12 years. As more and more things get connected, they need a way of efficiently communicating. And MQTT is seen as one of those protocols to enable that to happen. So there's some advantages and disadvantages for using MQTT. It's an OASIS standard. It's extremely lightweight. It's been designed to be embedded, placed on embedded devices and have a very small footprint itself. The message payload is very kind of slim and opaque. It's basically, the header itself is a couple of bytes. And the payload is just a byte array. And it's also built into a number of different projects: Mosquito, ActiveMQ and Apollo. WebSockets has a plugin for MQTT, and RabbitMQ is supporting this now too. There's a few disadvantages. Currently only supports publish subscribe. 5.0 of MQTT will support queues as well, but that's still being drafted, and that's probably going to be some time away before that comes into becoming a standard. The other one is AMQP. ActiveMQ recently adopted for 5.8 1.0. And we did that adoption through Apache Cupid. Cupid has a sub-project called Proton, which enabled us to pick up AMQP compliance fairly easily and fit it into our message broker. Now, the advantage of AMQP is it is kind of being like the default messaging protocol for all message brokers, which you will come across in open source or community-led, etc. The only downside is, if you look at all the messaging systems out there currently, most of them are using WebSockets, and that's about 70% of the market. Probably more like 5% is probably TIBCO and some others. But the big established players have no reason to move to AMQP yet. But the more people who use AMQP and ask for AMQP will hopefully force WebSockets or IBM to move to that as a standard. And finally we have, And finally we have Stomp, which is extremely easy to use, and it provides a lot of connectivity options for us. It's kind of a de facto standard. It's been adopted by Rabbit, the Stomp server. OpenMQ from Oracle uses it. ActiveMQ has been using it for a long time. And one of the advantages is it's so easy to define a messaging protocol with it. So much so that you have languages like Perl, Python, PHP, JavaScript using it for clients. So here's an example of using Stomp with Ruby. As you can see, it's very straightforward, and it only expects to have a payload as text. So you can encode, obviously you can encode different sorts of payloads into text, but because it's so simple and lightweight, it means that you can get lots of different clients using it. And there's an advantage for doing that because ActiveMQ also supports WebSockets. And Stomp is a natural wire protocol for WebSockets, because if you want to do a messaging kind of paradigm on top of WebSockets, because Stomp is text-based, it will support JSON naturally as a payload. But you can also do things like subscriptions to particular queues or topics. You can support all the basic messaging concepts I talked about before. Wildcards, selectors, etc. are all supported by the Stomp protocol. So you get the richness of a messaging protocol laid on top of WebSockets. So this is an example of configuring those transports inside ActiveMQ. This is, if you look at the ActiveMQ configuration, which is usually just an XML file, it basically lists a number of different connectors, and we can support secure WebSockets, AMQP. There's options on there for supporting NIO if you want to, and then you can mix those up with SSL, so you can have AMQP plus NIO plus SSL. And you can have all those protocols running at the same time inside an ActiveMQ message broker. So straight away you have ActiveMQ as a conduit, a router for different messaging systems. You can connect Stomp, WebSockets, OpenWire, MQTT and AMQP all from the same message broker. And that's a powerful concept when you think about integrating everything. If you've got an enterprise which is looking at getting information back from its stores, and we have customers who do this, thousands of stores. They want to know what's going on at the point of sale on the tills, what the inventory is like. They want to send that information securely and reliably back to their head office. But also they want to mix that information in with where the delivery trucks are going to be. And the delivery trucks are using an unreliable protocol, but they'll be using MQTT over a satellite link or GSM, or depending on where they are, they're flipped between different transports to send those messages off. But at the back end, they can use ActiveMQ to collate all those messages and provide all the information back to the head office. So let's talk about some management concepts in ActiveMQ. ActiveMQ comes with some command line arguments. So the ActiveMQ script, that shouldn't be capitalized, it should be lowercase a for ActiveMQ. It just runs a broker. And there's some command line scripts for managing the broker, stopping it, querying it, finding out statistics on it. You can browse queues, you can list all the connected clients on there, etc. You can also interface to it with messaging too. So this is an example of actually using a particular internal topic to get information back from a message broker. And you can find out statistical information on the broker. You just have to set the reply to message on the message you send to the broker. It's just an empty message. You send it to the ActiveMQ statistics broker. And then if you want to actually find out information about a particular destination, you'd use the syntax in red, and there's an example in blue, e.g. Q, ActiveMQ statistics, foo, where foo is the name of the destination. And there's a wildcard on the end, so any destinations which are named foo dot something, you would receive all the information back from them. Now ActiveMQ comes with an embedded web console, which is fairly basic, and we're going to be replacing that soon in the next release with something called Hotio, which is far better. And if I get time at the end of this presentation, I might show you a demo of that. So moving swiftly on. There's also enterprise features that ActiveMQ has, which are essential if you're deploying into enterprise scenarios. You need things like failover, you need connectivity across data centers, etc. So the first thing I'll talk about is high availability. And we provide high availability through master-slave clustering. And it's an active-passive model that we rely on. So when you send messages to the master broker, if that dies, both the producer and consumer will get connected back to the slave broker, and you'll receive messages from there. A common concept we have to rely on, though, is that disk, which could be a shared database, but it could be a file system, both the master and the slave, or slaves, have to get a lock on that shared storage. So if it's a database, that's fine. We've already got, we can already do a shared lock, and that comes out of a box. If it's a file system that we're sharing, then we assume that that file system is going to support shared locks. So that's, you're then restricted to using NFS version 4.2 or higher, or GFS, to provide that shared lock. I'll talk more about how we're fixing that later on. So something else we need to do is provide wide area network connectivity. And we need to provide things like you've got a cyclic network between your data centers, and you also need to support situations where a link will go down, and you want to still be able to route messages between different data centers. Maybe not the most efficient way to do it, but at least if you've got connectivity there, then you ideally want ActiveMQ to sort that out, and it can. It can do that out of the box. And we use something called networks of brokers to do that. Networks of brokers is really the same as store and forward. We provide store and forward between different remote brokers. They only share one connection between the brokers, but something as well we have to take into account is when you've got, because it's store and forward, when you've got remote brokers in different data centers, ideally those brokers on each end of a data center has to be clustered, as in this scenario here. So it starts to get a bit messy because not only does your master have to know about the opposite master to connect to, it also has to know about the slave to connect to too, and vice versa. So you start to get into a bit of a configuration mess. Another problem is brokers with ActiveMQ, they share all the information around between the brokers on the networks. So every destination is global, which means if you've got thousands of brokers, that's an awful lot of chatter. Every broker is telling every other broker on the network who's just connected to itself locally. I've got all these consumers and these queues. Are you interested in sending messages to my consumers? And the other brokers will take reference of that information, store it away in their internal data structures. And if a message does at some point come up to be sent to those remote consumers, it would be routed to those remote consumers. But there's then an issue of scale. You get very chatty networks. And you can partly solve that with ActiveMQ. You can do some traffic shaping, so you can do filtering on the network connections themselves. But that involves a lot of manual configuration. So let me move smoothly on. Which is why, sorry I'm skipping past, I'm running out of time. Which is why we use something called Apache Camel. Who's heard of Apache Camel? Good, okay. So you don't need me to explain Apache Camel to you too much. You know what that is. So a key thing, though, about Apache Camel, and it actually came out of ActiveMQ as a project, as a sub-project of ActiveMQ, is that we allow the embedding of Camel routes inside the message broker to provide flexibility. So just to show you some code examples of that. This is like probably the most basic configuration you can get for an ActiveMQ broker. And at the bottom in red, you can see we're importing a Camel resource. And this is a very simple, straightforward Camel route. It's a choice, it's a when. So when we receive messages from particular queues, we can route them based on their content. Assuming that content's going to be an XPath, which in this case it will be. So using that concept, we've been able to deploy in reality into production scenarios where customers have used thousands of message brokers, not by relying on networking alone, but by combining that with ActiveMQ to actually do the traffic shaping for us. There's some other issues though. Installing brokers on multiple hosts is time consuming and it's costly. You have to copy lots of configuration files around. When you're copying configuration files around, you then have to rely on things like best practices for versioning, etc. I mean, when you upgrade brokers, that also becomes a problem. It's very tedious and it's an error-prone process. And this is one of the biggest problems you have with any kind of large-scale deployment, unless you have something in place to help you do it. And we do have some best practices like these. Yippee-hoo. But there's this project called Fuse Fabric. Has anyone heard of Fuse Fabric? A couple of you heard of Fuse Fabric. Fuse Fabric was something developed by FuseSource. It lives at GitHub. It's Apache licensed. And I'm mentioning this today because it was it's the foundation of the products we used to do and still do as part of JBoss at Red Hat. But we're moving these to the Apache Software Foundation underneath Apache Service Mix. So what's Fabric? In a nutshell, it provides a centralized distributed broker configuration. We use Zookeeper currently to provide that centralized broker configuration. Currently, we're using that really for liveness. Actually, the configuration itself lives in Git. And we have Git clients which can interact and pull back the latest configuration which they need. So there's three parts really to a fabric. I've got it on this diagram here. There's a runtime registry. There's a configuration itself which can live like anywhere. And then there's the endpoints which rely on an agent running to actually know how to talk to a registry, know how to interpret the configuration, and then it deploys stuff. We also have some tooling. There's Fuse IDE, which knows how to talk to fabrics. That itself, that's at GitHub. It's Eclipse license. It's open source. Please have a look and have a play with that. So we have some special concepts which are built around the Fuse fabric. And one's called a Fuse MQ profile. Fuse MQ is really just ActiveMQ deployed in Apache Carafe. But it defines some extra features too. It knows how to do things like create connections to other brokers, other Fuse MQ brokers, relying on the Fuse fabric. It knows how to create networks between brokers. So suddenly, from going over from this manual way of doing configuration, you have this ability to do things a lot more centrally and a lot more straightforwardly and easily. And you can also maintain things in a much more consistent way. So this is an example of creating, this is from a command line, Fabric, the Fabric shell extends the Apache Carafe shell with additional commands. One of those being the ability to create a cluster or container. And this command is basically saying, I want to create a container. I'm going to call that container broker 1, and I want to run a Fuse broker onto that broker 1 group or cluster. You can also assign profiles as well. So you can assign profiles to running containers too, which means it's very easy to update things. So now we can easily create new brokers anywhere, where the fabric's deployed, and the fabric can be deployed on premise, on your local laptop, on a cloud environment. And it also means you can easily update all these brokers from one central place. We also provide the ability to provide profiles, so you can mix and match things together. You don't have to just deploy ActiveMQ. You could deploy ActiveMQ with certain Camel routes if you wanted to, or service mix, or anything else that Fabric supports, or as an OSGI feature or bundle. Once you have that concept in place, you can also do things like then roll out to your whole environment upgrades, be they patches to particular bundles or jars, or upgrades in configuration. And you can also roll things back if things go wrong too, which is also very important. Let me start this again. So because the registry knows where all these containers are, when a Fabric node starts up, it's kind of like a vanilla agent. But when it reads its profile, it starts to build up a software which exists on that agent, be that ActiveMQ, Service Mix, Camel routes, Tomcat, Tommy, JBoss, whatever. It registers back as well with the registry. So the registry knows where it's physically really located, which makes connecting to ActiveMQ brokers very easy indeed. It means that you can just, instead of knowing where the physical URL of a broker is, you can ask the fabric to do that for you. So in this example here, using a connection factory, I'm using a discovery protocol, which is a fabric discovery protocol, and I'm asking the fabric to give me a connection to a group. And the default group is called default. So that means you're already taking away, not only on the broker side, but also on your client side, the needs to be able to be to know where the location of brokers are. So this allows for some interesting topologies as well that we can deploy, because ActiveMQ agents are also clients of Zookeeper or our registry. So you can do things like create clusters with one command. And there's also a web console as well, which enables you to do this. And it also enables you to do things like create networks too. So that first command is creating a cluster group called US East. And it's deploying containers, US East 1 and US East 2. And then it's setting up US East. The last argument is actually the name of the broker it's going to start running. So that's going to pull up and start running on that particular group. And similarly, down below, you're telling the other group on your west side to start up too. But the key thing there is the networks command. You're telling it what group to connect to and deploy networks on your behalf. So instead of going through the hell of having to do all these complex configurations of knowing where across the network where all the slaves are in your configuration file, you can do it all now with like 2 easy commands, and it's even easier using the web console. So to summarize, as integrations got more complex, there's more things we need to integrate with, not only in terms of SaaS providers, not only internally, but also in terms of a number of devices we need to connect to. We need a whole ecosystem of different technologies to enable you to do that. Message brokering is key. So having a message broker which is multi-protocol is certainly going to help. But then having things like Apache Camel at both at the edges to enable connecting into different protocols and is certainly beneficial. And ActiveMQ and Camel are first-class partners in that regard. ActiveMQ has, out of the box, has a component which speaks to ActiveMQ extremely well, more efficiently than the JMS component. But in addition to that, you also need a way to manage all these things together. And the fabric, Fuse Fabric, allows that to happen. Now, when Fuse Fabric actually, when that moves to the Apache Software Foundation, its name will be changing. We haven't decided yet on what that name will be, but Apache needs to make sure it can actually trademark a unique name, something you can't do with Fuse Fabric. So, 7 minutes of questions. Any questions? Yes, sir. So the question is, if you had just one message broker, how many queues could you put on it? And actually, there's no, well, the limitation is actually the amount of memory you have. So internally, a queue or a topic, a queue is actually slightly more complex. There's more configuration options around it. But actually, a queue is just, it's a small object itself. So you can scale up the message broker to hold more queues. In addition, in ActiveMQ, you can also define how much memory that queue will take up. Because queues will cache messages on the queue as well. Okay, thank you. Do you mean memory like RAM or memory like this? Both. So you can scale out you can tell ActiveMQ, I want to only store like 1 megabyte in memory. If you've got non-persistent messages, then spool those over to disk. So you can configure how much of that temporary disk storage for non-persistent messages you want to take up. By default, that's a gig, but you can configure that too. And then you can also configure ActiveMQ to say how much persistent persistent messages, I want that disk space to take up too. And when you reach those limits get sent out as alerts. You start to push back on the producer as well, who is sending you messages to. Any more questions? Anyone want to see a demo? Yeah? Okay. A day or week or second? Yeah, so for persistent queues, we have done north of 30,000 messages a second. It really sorry? 30,000? So this is the console I talked about, which is going to be the next console in ActiveMQ. It's called Hotio. I'll have some links on the end and of my presentation, which I'll flip back to. But you can find Hotio on the web. Is it gone? Can you not see my demo? Okay, so this is going to be the dashboard. You still can't see it. When you come around and look at my laptop quickly, I'll show you afterwards because we're running out of time. Any other questions? How far can you, sorry, can you?
How far can you actually scale down the system, for example, embedded system, for example?
Scale to embedded systems? Yeah.
I mean, I know that MQTT has some very small breakers.
Yeah.
I mean, what's the kind of minimum configuration?
Well, MQTT comes with a raft of different client libraries. ActiveMQ uses a Java-based one, which obviously you wouldn't really want to use on an embedded device. But the Eclipse Bajo project does come with MQTT clients, and they range from a few hundred K, which is to less than that. It's just a binary protocol, so it's very small. But if you want to, in terms of connecting outwards, you then have to look at probably more advanced architectures. And we do things like, we provide kind of like routers to fan up messages from MQTT. So usually one single broker instance or a router moves messages up, will do it in a tree. And one of those could handle between, depending on the configuration, between 10,000 to probably 100,000 connections, which isn't very many. So you need to run probably a few of these. And there's an example of somebody doing this in the US for set-top boxes. They got MQTT running on a set-top box, and they got that there because they want people to be able to change channels through mobile phones. Mobile phones, you'd be using HTML5 clients, send back the request to the end server of the back office. The back office will then have to send that message back over MQTT to get the performance. Because when you change a channel, you don't want to wait a few minutes for that to happen. It's got to be instantaneous. Okay. I can show you on my laptop. Okay. Thank you. That's it. Thank you. Yeah, I'll show you this.